valence shell electron pair repulsion theory is a starting point chemists use to determine the molecular shape of molecules. So one of the challenges we have is coming out of Lewis structures is that there's a lot of different ways we can arrange those peripheral atoms around that central atom. And we said all of these Lewis structures would be correct. And how can that be? Because when we look at these, there's different angles between the bonded atoms, and we know when we look at ammonia in nature, that's not the case. When we looked at Lewis structures, the information we got out of them was not about the geometry of molecules, it was the connectivity of atoms in a molecule. So all three of these show each hydrogen atom is bound to that central nitrogen, and that's the important information out of these Lewis structures. So we need some other way to take this Lewis structure, the information about this connectivity, and then use it to predict the geometry of these atoms around that central atom. And for this, we'll use this valence shell electron pair repulsion theory. And it basically operates under the idea that electron groups around an atom repel each other. So the negative charge of these electron groups repel one another, and so they're going to position themselves around that central atom in such a way as to get those electron groups as far away from one another as possible. And that this repulsion determines the shape of bonds around that atom. So in electron groups, there's two basic categories. There's bonding groups. I'm going to label them as bonded atoms. And there's non-bonding groups, or lone pairs. Now it's very important. This could be single, double, or triple bonds. All are going to count as a single bonded atom, a single electron group. So to look at what this looks like, I'm going to use the PhET molecular shape simulation. If you just Google that simulation, you'll come up with the link I've typed in there. Okay, so in this simulation, it's basically letting us manipulate and look at bonded atoms. In this simple example, I have two electron groups, two bonded atoms, and they've positioned themselves so they're as far away from each other as possible. Now, because they're stuck to that central atom, it's just changing the angle. But at 180 degrees, that positions those clouds of electrons as far away as possible. And so this would have a linear geometry. That's the name we give to this arrangement. If we had another bonded atom, the way they can get as far away from one another as possible is to position themselves in a plane, but at 120 degrees from one another. It sort of looks like a Mercedes-Benz symbol to me, but however you want to remember it, the name we give to this structure is trigonal planar. So they're in a plane, and if you sort of draw a shape around those terminal atoms, it's a triangle, trigonal planar. Okay. Now, when we add a fourth, we don't get a square planar shape like you would get if you drew on paper. So if we're drawing methane out in the Lewis structure, you probably ended up with something like this with 90 degrees between the bonds. But if we allow the molecule to go into 3 dimensions, it can spread out a little more. It can spread out by forming what we call a tetrahedral geometry. The atoms form the vertices of a tetrahedron, and in this shape there's 109.5 degrees between each of the electron groups. And so that's a little more than that 90 degrees. And this 3-dimensional structure that we get, this tetrahedral structure of that central atom, is incredibly important in understanding activity, chirality of many molecules, and particularly for biologically important molecules and drugs and understanding those drug interactions. This 3-dimensional shape is very important. Now, something interesting to note here, if I have 3 electron groups, it doesn't matter if one of them is a double bond. I still get that same 120 degrees. It doesn't matter If one is a non-bonding pair of electrons, a lone pair, we still get that same 120. But when we have a lone pair, we don't talk about the angle between that lone pair of electrons and the bonds. That's not something we can see in crystal structures. So we talk just about the angle between the bonds. Okay, so we can put the information we get into a table like this, and this is a useful reference if you're working homework problems or exams. It's something you can memorize. But the first step in looking at molecular shape is to take this chemical formula, draw a Lewis structure, and use it to determine how many electron groups we're talking about. The number of electron groups determines the electron geometry. So if we have 2 total electron groups, we have a linear geometry. That was like the 2 bonded atoms positioning themselves 180 degrees away from one another. Now, we don't talk about a geometry if there's 1 bonded atom and 1 lone pair, so that doesn't really appear in this table. So there's one option with 2 electron groups, that's 2 bonded atoms, linear. Both electron geometry and molecular. If we go to 3 electron groups, the electron geometry is going to be trigonal planar. And in every case, if all of the electron groups are bonded atoms, the molecular geometry will have the same name, trigonal planar. But if I take away one of those bonded atoms and replace it with a lone pair, it's like one of the spokes is missing, we're going to give it a different name. It's going to be called bent. Okay, so boron trifluoride is an example of trigonal planar. Formaldehyde would be another example. Sulfur dioxide or the nitride ion are examples of things with a trigonal planar electron geometry but a bent molecular geometry. If we go to 4 total electron groups, we're going to call it tetrahedral electron geometry, and if they're all bonded atoms, a tetrahedral molecular geometry. So methane is a classic example of a tetrahedral carbon. If we replace one of those bonded atoms with a lone pair, that would be something like ammonia. Okay, and it's going to be what we would call trigonal pyramidal. We've replaced one of those bonds with a lone pair. That central atom is slightly out of plane for the 3 hydrogen atoms, slightly raised above it, so it forms a little pyramid. And water is the classic for if there's 2 lone pairs and 2 bonded atoms, we're going to call it bent. Now notice there's 2 geometries that we give the name bent to. One has a bond angle of about 120 degrees. The other has a bond angle of 109.5 degrees or close to it. So this is just vocabulary we use to describe the shape. And we can apply the shape in the small types of molecules you would be drawing with Lewis structures in a general chemistry course, but we can also use this theory to evaluate the shape of atoms and molecules. And when we do this, we're not going to look at the shape of the whole molecule using VSEPR. We're going to look at the shape of a specific atom. So if we want to determine the shape of that carbon, we would look at that carbon in the structure and we'd say there's 1, 2, 3 electron groups around it. Remember, the double bond counts as just 1 electron group. And if there's 3 electron groups, it's trigonal planar electron geometry. In this case, they were all bonded atoms, so it's also trigonal planar molecular geometry. We could then go to another atom. Maybe we'll go to this nitrogen here. This nitrogen has 1, 2, 3 electron groups. So it's a trigonal planar electron geometry, but in this case, one of those groups is a lone pair. And so we get the bent molecular geometry. Let's look at this carbon here. In this case, there's 1, 2, 3, 4 electron groups, and it would be a tetrahedral electron geometry. And because there's no lone pairs, because they're all bonded atoms, it would be a tetrahedral molecular geometry. And just as a word of caution, VSEPR doesn't work all the time. So if we look at this nitrogen, what VSEPR would tell us is 1, 2, 3, and that lone pair would be 4 electron groups. And that would say it should be a tetrahedral electron geometry and a trigonal pyramidal molecular geometry. In practice, if we look at this structure, this is caffeine, that nitrogen is planar. And something is going on here where that lone pair of electrons is influenced by what's going on nearby atoms, and you can learn about and understand this better using hybrid orbitals, hybrid atomic orbitals. So just a word of caution, there are places this breaks down as you get into larger molecules, but the process for using VSEPR to evaluate shape is start with the chemical formula, get a Lewis structure, look at one atom, you're doing the shape around a particular atom, and use the number of electron groups split into bonded atoms and lone pairs to identify the electron and molecular geometries.